Zarnescu. I think you were here for the first workshop, is that right? In January?
Yes.
And so he's just started another period here of a few weeks, and he's going to give us 2 talks this week, today and tomorrow. And this is the first one. You can see his title, and I'll up to you now.
Thank you very much, and thank you for coming. So yeah, I signed up for 2 talks, and now I'm kind of worried, why did I do that? But you'll notice that in both titles there is this either mathematical or mathematician, which should be read as code for, I don't really know much of anything about liquid crystals. My love affair is with PDE, partial differential equations, and I have some hopes that they are the right ones for describing liquid crystals. And it's actually worse than that. I'm one of those guys that believe that studying a PDE is like a contract with the devil. Namely, you can sign up for it, but once you chose your PDE, you should stick to it and don't arbitrarily throw away terms in order to make the PDE tell you what you want. Okay, so these being said, I still hope to ask some physical questions. So, if you feel that I'm getting too far away from that, please tell me, and in the future I'll try to get closer to the physics. Now, I have this thing. A little bit of modeling so that you know what kind of liquid crystals I'm talking about. This is all stuff that I learned from Nigel's paper about Q-tensors. So basically the ones that I'm looking at are the simplest ones, rod-like, and the main characteristic, that is the fact that these rod-likes are locally aligned in space, as you know, can be modeled by a measure, a probability measure at each point in space. So this is something which associates to each region of the unit sphere a number between 0 and 1, and that number is supposed to tell me what is the probability that molecules are pointing in that region A on the unit sphere. And since these have no head or tail, the molecules, you have this physical requirement that mu of A is equal to mu of minus A. Okay, so at each point in space, you are supposed to have this monster, and that should give you a pretty good description of what happens in this type of nematics. Of course, it's also a very complicated description, so apparently it's their responsibility for looking at something simpler, namely this second-order moment matrix of this measure, because the first-order moment vanishes, so the second-order moment is presumably supposed to capture most of the content of this measure. Of course, if this measure is uniform, so there is no preferred direction on the unit sphere, you get exactly 1/3 of the identity. So overall, this object that you produce, like here, which is a 3x3 symmetric and traceless matrix, is supposed to give you a crude measure of how far you deviate from isotropy. But in doing this, in working with matrix at each point in space instead of a probability measure, you threw away a lot of information, right? I mean, as an analogy, if it's like turning a periodic function into just its second Fourier coefficient for, in the Fourier expansion. So you lose a lot of information. There are plenty of very different measures that have the same Q-tensors, right? So now that's pretty bad because there is this curse, if you want, of low dimensionality. If you force your model to be low dimensional, maybe you lose some physical characteristics that only a more complicated higher dimensional model should be able to, could be able to describe. But nevertheless, from a mathematical point of view, this is quite great, and I can confess that I worked during my PhD, on this perspective with probability measure, and that's so much more complicated, while this is so much nicer. So from a mathematical point of view, this is nicer because it has structure encoded in it. There are various symmetries and geometry that comes with working with matrix-valued functions. If you were to consider the basic analogy between working with real valued functions with values in R2 or complex valued functions, the complex valued functions are much nicer. They have various symmetries encoded in them. They know how to do tricks that real valued ones don't. So in some sense, it's like this in here. Once you start working with these kind of objects, you get a lot of interesting mathematical benefits. But there might be a price to pay in the physics, this low dimensionality curve that I mentioned. Okay, so there's some terminology that I'm going to use again and again. So these matrices are called isotropic if it's just a matrix with zeros everywhere. Uniaxial if it has two eigenvalues, and biaxial otherwise. And my understanding is that there is an optical signature for this terminology. Okay, still working with matrix-valued functions is a rather complicated thing for mathematicians. Although this theory was proposed in the 70s, it didn't really take up with mathematicians until the 90s. So Ericsson in 91 was suggesting this theory for uniaxial Q-tensors. So if you look at a matrix that has two equal eigenvalues, you play a bit with linear algebra, and then you realize that you can write it in this form, where S is a scalar, and N is a unit vector. And actually, at that time, Ericsson was aim was to extend the best known and nicest, most studied theory, the Ozin-Frank theory, right? Where formally you take this S here to be space independent, just a fixed constant, S plus. So, right, you have all these possible descriptions for the same physical object, right? In here, in Ozin-Frank, you have just 2 degrees of freedom. You work just with unit vectors. Here you have scalars and unit vectors, so 3 degrees of freedom. So for all practical purposes, Ericsson worked with this, not with the matrix correspondent, and there is a difference. Or finally, you could work with objects that have 5 degrees of freedom, right? So what's the best thing to do? Well, if you work with simpler objects like in here, you definitely have simpler equations, right? But maybe you miss something. There is this curse of low dimensionality, right? And here, this is manifested in the topological constraints. Okay, so in principle, since you started playing this game, 2 degrees of freedom, 3 degrees of freedom, 5 degrees of freedom, why not go even further, right? And somebody will come in a couple of years and say that they want to work with 2 or 3 types of Q-tensors and so on. And this actually happens, right? So where should you stop? What's the right point in this complexity hierarchy where you should stop? Well, my interest is in understanding what are those features that require a tensorial description. Namely, if you were to work with one of these 2 descriptions, you would miss some essential features, right? So I'm trying to understand, what are those essential features that only this kind of description would be able to provide. But there is this general question, what is the most appropriate description? And there are 2 issues that need to be balanced in choosing the appropriate, description. There is something which is rather obvious. If you have more complicated objects that you use for description, you'll do better at smaller scales, right? So there is this defect in the Ozin-Frank type of theory that looks pretty much similar with what you'd get in the Q-tensor theory, only at the exterior, right? The interior core is different, right? So my understanding is that this is what some people mean when they say that the Q-tensor theory describes things at a mesoscopic level, while the Ozin-Frank describes things at a macroscopic level. Okay, so this is kind of obvious. I mean, okay, you wouldn't be surprised, right? If you use a more complicated description for liquid crystals, you get a better description at a small scale. But you pay a price. This price that I was calling low dimensionality curse is sometimes appreciated as something good, and comes into the form of global constraints, the topological constraints, right? So for instance, this is a typical case where you see these topological constraints. If you impose Hedgecoe boundary conditions on the unit pole, and you try to extend those boundary conditions inside with some tensor field, yeah. If you try to do it with vector fields continuously, then one necessarily finds an isotropic melting point. Otherwise, you would contradict the fact that you have a degree 1 boundary condition here. So this tells you that essentially that because you use too simple an order parameter space, they cannot pack quite arbitrarily, and this is synthesized in these topological constraints, right? So if you work with an order parameter that is too simple, you get these topological constraints, which might be a fake, right? You just get them because you use the wrong mathematical description. On the other hand, if you use Q-tensors, you can avoid this isotropic melting, right? You just choose something like this. So you can construct an extension like that would look, say, roughly like the biaxial torus, which doesn't require isotropic melting. So if you use this more complicated object, the Q-tensors, instead of directors, you relax these topological constraints. You have more freedom to match things in a continuous manner, right? Nevertheless, there is some topology left in the Q-tensor representation, but it's much more subtle business. And unlike in the director case, you don't have a quantitative understanding of this topology. In the director, you have a formula for the degree, so that allows you to do various tricks, while for the Q-tensor, you don't. So you just have topology. So things are much more subtle when it comes to the Q-tensors and what they do at large scales, at the level of topology. Okay, so this is so far just about choosing the right mathematical object to describe the things and what benefits you have and what troubles you have. Now, this is the real trouble, because I told you that I like to study equations, and there are quite plenty of them, too many, and of various kinds. If I were, say, to draw this imaginary vertical axis of complexity, yeah, you have these very complicated models somewhere, above my head, which combine something like temperature, fluid, velocity directors. You can add electric fields, and you can write these equations either with the director theory, Eriksson theory, Q-tensor theory. You can go, even more complexity, use the probability distribution function. If you are not happy, you can try to describe things at a molecular level, so that gets even messier. So you have these very complicated objects, and there are like two lines of attack you know, on one hand you have the continuum mechanics people that like to write these equations, and then you have people like me who write to prove that they have solutions. So you know, that's what I was doing last week. After you do that, what do you really understand out of those very complicated equations? Well, nothing. So you know, what people do in general after writing those equations is to say that okay, there are these very complicated equations, but you know, we'll take now a toy problem. We go to a simple geometry, then the equations become very simple. So as the level of complexity, they decrease somewhere here, yeah, and you get like a system of coupled ODEs. You can simulate that, and you're happy. And for all practical purposes, this is where you know, the real action happens, because this is where the applications for displays are, right? At the level of these simple models, yeah. And then there are some fake things between these simple realization of the complex models and the complex, the real thing that is here on top on complexity. And there are various, you know, more or less fake models which you obtain by dropping arbitrarily temperature dependence, flow dependence. So if you do this, now you are left with something just directors, and you get equations that say you want to drop time as well. So you get the simplest kind of systems out of those that you know, just use a variational theory. Yeah, no time dependence. You minimize the energy, and still that is supposed to capture some physics, some of the physical behavior. But nevertheless, all these level of descriptions are kind of fake. The real thing is just up there, but you cannot do anything with it. So nevertheless, we can only understand, for all practical purposes, simple things, right? And even with computers, you're not doing much better. You still want a simple model that you can analyze. So you know, is there a consistent way of getting from you know, the complicated things that you don't understand to some tractable, you know, simple equations? And of course, there is this natural way. You just impose you know, enough conditions, a simple geometry, and the equations simplify. But you are losing a lot of you know, possible good things that the liquid crystal could do in all this range of complexity. So one thing that you could do is to obtain out of those very complicated models simpler ones in a consistent manner. And by this I mean passing to the limit in some limit cases. So that means that you need to determine some specific features that you know, are of interest to you and that need to be overemphasized in some limit. So I'm going to do that in a very simple model, of course. Nevertheless, I think that this should be like you know, a larger goal, and that's where, you know, physicists and mathematicians like me can interact fruitfully, because you know, the physicists have the right intuition at what is the right limit to get out of the more complicated systems. And you know, people like me make a living out of passing to the limit. So let me you know, try to show you what I want to pass the limit into. And of course, I'm just going to do my favorite equations, which are of course the simplest ones. So as I was saying, somehow the simplest model that still seems to be capturing some physics is this one. You try to minimize an energy functional like this. Now, one elastic constant with the simplest bulk term you can put, and pray that this is still able to tell you a physical story. What you get is an innocuously looking system. So it's only specific, I mean, non-trivial feature is the fact that it's a system. I'm going to tell in a few moments about the constants here, but for now just about the PDE. And I'm going to put boundary conditions which are of the Ozin-Frank type, but written in this tensorial form. And I'm going to choose the boundary conditions to lie in the minimum of this bulk potential. Okay, so like this. Sorry, so this is the minimum set for the bulk potential, and then boundary conditions will lie in this minimum set. Okay, so what would I like to do with this? I would like, as advertised, to be able to say something that is relevant to physics, although that rarely happens, but one hopes. Okay, so defects, right? That's about the only thing that mathematicians know about. There are prettier pictures nowadays of defects. This one is from 73 of Zope, and the only purpose that I like this one as compared to the others, I mean more, is because here it told me, you know, what's the magnification of this image, right? So I have an idea of how big this image is in practice, and it seems to be somewhere between 1 millimeter and 1 centimeter. Please correct me if I'm wrong. Now I like that because then I know all the other parameters for MBBA, and I can try to understand what this picture defects is about. So what do we have here? Now we have this elastic constant, which is something like this. We have this material-independent coefficients, which are, you know, of the same order of magnitude, but with these joule per meter cube units. And then you have this temperature-dependent coefficient here. Within 10 degrees of this supercooling temperature, which is the temperature where the isotropic phase loses stability, you know, this A, so if I denote this whole thing with A, is of the same order with B and C. And now, the way I want to non-dimensionalize is such that I understand the picture I had before, right? So I want to think of that picture as being on a square of length 1. Yeah. So I express my units in terms of the length of the length scale of that picture. Yeah. And I obtain this kind of energy functional. Okay. And now all the terms in that energy functional are in the same units, joule per meter cubed, and you know, I decide to divide by this k, and this way I obtain a non-dimensional representation for that energy functional, where now I'm going to formally leave these with the same names. Well, this will be called A. This will be called L, B, and C. But from now on, they will all be non-dimensional. And so the ones with heads are non-dimensional, but I'm going to drop the heads soon because I don't like to carry them along. And the important thing is that here the elastic constant is 10 to minus 7, and all the other coefficients, A, B, and C, and the size of the domain is size 1. Okay? So this non-dimensionalization is for the purpose of understanding that picture with defects, right? So, well, you get this small parameter and you are happy because, you know, some people like to pass to the limit. And, well, formally there is no physical limit because if you let L to become infinitely small, there is nothing left there. But what you get is an asymptotic expansion, which makes sense for L very small. So you get something like this. So if I denote by QL the energy minimizers corresponding to a fixed L, then I have the formal limit, and then I have some small correction. Yeah? Okay, so this is my non-dimensionalization, there are other non-dimensionalizations, of course, plenty of them, but you know, some people that taught me about these things, well, Chuck in particular and Epifanio, they consider different non-dimensionalizations. So they express the length in terms of units relative to the size of the defect cores, right? So these size are the lengths of the defect cores, or the biaxial coherence lengths overall. So what happens if you do non-dimensionalization in terms of those units? What you do for all practical purposes is to focus your, don't know, whatever microscope use, or to focus your image only just on the core, right? So instead of studying the whole thing, you want to study just what happens near the core. So these non-dimensionalizations are very good for studying the core of defects, and that's, you know, exactly what they were studying in these papers. While the other non-dimensionalization that I was doing here is good for looking, you know, I think this picture where defects are seen as being small. Yeah. So I think we agree now on the non-dimensionalizations. And actually, it will turn out that in my non-dimensionalization, the defect cores are of the order of square root of L. So that's the biaxial coherence length in my non-dimensionalization. Okay. Now, these being said, let's move to what we have now. Okay. So here I should have put an A, B, and C because I want to consider things at fixed temperature. And also, I'm thinking, you know, from now on everything here is non-dimensional. So what happens if I try to analyze what this energy functional can predict? Well, for one thing, I see that this is bounded from below, and the minimum is attained at a negative number. So that's not quite nice. So if I add some positive thing, I can get this FB tilde. Yeah. So if I just add a constant to this energy function, the energy minimizers won't change. But what I get is a bulk term that is positive. And I want to do that because instead of studying this energy function with the L here, I can divide and get this energy functional. Well, this bulk term is positive. And I was saying that I want to study what happens with the energy minimizers here when L is a very small constant, right? So this is a positive thing. So when L is very large, I would like this thing to be 0. Yeah, this thing is 0 exactly when you are in this Ozin Frank.
L very small or very large?
Sorry?
You said L very large, but you mean...
sorry, L very small. Yeah. So, you know, when L is very small, in order to minimize the energy, I'll be very happy if everybody stays in here. Yeah. So, given that this S plus is a positive constant that you can explicitly compute in terms of these parameters, what matters here is just this N, which is a unit vector. Yeah. So, this is pretty much Ozin-Frank. Yeah. And boundary conditions are chosen to agree with this, so that I can compare the Ozin-Frank theory expressed in this form with matrices with this Q-tensor theory. Yeah.
Excuse me. In this case, the top expression diverges.
Sorry?
Diverges. Top expression diverges, and so you try to subtract.
No, it does not diverge.
Finite.
Finite.
What are you doing at this moment? Subtracting some positive number.
I'm not changing anything. If I subtract a constant, that will... sorry? Why am I doing that?
Motivation to subtraction minimum FB.
I want to make this positive.
Just a sign.
Yeah.
Wow.
Because then, you know, if I divide by L and I put here L on the bottom, if this is non-negative, I mean, if this is -5, yeah, and I divide by L, this will go to -infinity when L goes to 0. If if it's 0 over 0, better. Let's put it this way.
Again, I confirm. Quantity itself is finite, not divergent.
No, it's finite, yeah. So the rest is just mathematical trick to put things in a way that is convenient for me, for understanding things. Okay, so here's what you get. You denote by QL the global energy minimizer of this functional, right? So what the Q-tensor theory predicts you, and you want to understand what happens when that L, the elastic constant, non-dimensional, right, becomes infinitely small. So you get convergence to some limit functional, some limit Q-tensor. Don't worry about H1. That just means, you know, in the sense of the energy. So if you compare the gradients, the square, the integral of gradient squared. Okay, but the important thing is, what is this limit? Is a global energy minimizer just of this gradient part, but now I want to make that bulk part here happy, so I'm going to minimize this part here, just in the space in which everybody takes values in that set that makes this 0. Yeah. So H1 here just means that this quantity is finite. So otherwise said, Q naught should be of this form, where S is a constant and N is a unit vector, right? So if I formally put Q of this form in this integral here, I get this relation, and this is, you know, the one constant was in Frank, right? So this is to say that what I obtain in this limit is the Gaussian Frank, but expressed in this matrix form. Okay, there is a little bit of subtlety here when this is actually okay. Well, there is quite a lot of subtlety there, but I won't touch it today. That's work with John Ball. That's in ARMA. But let's see what happens with the global energy minimizer for finite, but small l. You have, after quite some work, you can show actually a better type of convergence, something like this. Yeah, QL of x and the limit, the Gaussian Frank, will be close. You know, so QL will be an approximation of order L of the Gaussian Frank almost everywhere, except some small regions, which should be read as defect cores, near the discontinuities of Q naught, the Gaussian Frank defects. Yeah. So if this is Gaussian Frank, you know that it has some defects, namely points where the director is not continuous, has a jump. Okay, so near those points of Q naught, this breaks down. But those are, you know, rare events. The defects in most of the domain, this is the Q-tensor approximation is an approximation of order L of the Gaussian Frank. And as I was saying before, in our non-dimensionalization, the defect cores have a size of order square root of L. We cannot really prove this. That actually seems to be pretty hard. So what do we have so far? We have this formal asymptotic expansion holds, you know, away from some exceptional regions in Q naught. Yeah. And Q naught, as advertised, is a way of writing Gaussian Frank using matrices. Okay. So let me try to draw something as to, you know, what happens. Have something like this. This is your domain, and I impose conditions, you know, that make sense in the Gaussian Frank theory. So directors, and I have for the energy minimizer various, you know, directors lying in here, and okay. So let's put n find omega values in S2. So these are the white things. And there will be some small points, you know, which are defects. These are like this. Yeah. Ozin-Frank defects. And you actually, well, there are some small regions, let's put it like these. These are of the order of square root of L, square root of L. If I stay outside of those small regions, the Q-tensor theory provides me with a good approximation. Okay, so in order to draw Q-tensors, I'm going to do these ellipses, you know, which are very thin, so almost near the Q-tensors, the directors. And so on, yeah. And I have that the difference between these and you know, the directors is so let's put it like this, order L. Yeah, so these are Q-tensors, and these are directors, unit vectors. Okay, so it looks like the whole action is concentrated here near the course of near the defects of the Ozin-Frank theory. Yeah. Okay, so what's happening there? We don't really.
I'm sorry.
Yeah.
You're thinking of point defects in 3 dimensions.
Yes.
Right. Not line defects in the.
No, just point defects. And the thing is that for Ozin-Frank theory, global energy minimizers and one elastic constant, well, equal elastic constant, sorry, the defects can only be point defects. And, you know, that's, you know, like a low dimensionality curse that Ericsson tried to avoid by relaxing the order parameter to a richer thing, unit vectors and scalars. Okay, so we don't really understand what happens here, but fortunately we have a lot of good intuition because, as much as I know, Tim Slukin first came up with this observation of a strong baxial structure, you know, in those green regions, and then several people did simulations that showed a very intriguing and nice structure, which looks like this, the so-called baxial torus. So this is some structure which is axially symmetric, so you are supposed to rotate that in 3D. Now, there are several simulations. Each one is a bit biased. This one here assumes this Luksetov constraint, which prevents you from going into isotropic melting. This one of Chuck assumes, you know, axial symmetry. This one, as much as I know, is the one that doesn't really assume many things, but all of them get qualitatively similar pictures. Okay, now there are very interesting questions and very hard. So, you know, for people like me that are interested in looking at these, here are some of them. I mean, I tried these with several people over a couple of years and couldn't do them, but they're very nice nevertheless. So, coming back to my drawing, what you have here is if I were to blow up you know, this region, yeah, and look at, I mean, it's like doing a non-dimensionalization in which I'm just interested in the defect core. There is this, you know, ring structure that you'd like to understand. So if those simulations are, you know, not biased in any way and everything is okay, then you should have the following thing. You should see a solution of this equation in the whole space with Hedgehog boundary conditions at infinity, yeah, which is axially symmetric. Yeah, you should find an analytic description of this biaxial torus. And if I just say that, then it's easy. There is a solution like that. It's called the melting hedgehog. That has actually more symmetry than just this axial symmetry. Yeah, that's a special solution which looks something like this, but you just let S vary. Yeah. So, it's interesting to see if we can find this analytical expression for the biaxial torus. And then there is this statement about universality. What happens near the defects in Ozin-Frank is something like this. So in Ozin-Frank theory, you have that defects are always like this. Yeah. So x over mod x this is the Ozin-Frank description, and near defect things look always like this. This is shown for global energy minimizers, equal elastic constants. So in that sense, you have this universal structure. Also, there are all these numerical observations which seem to say that, in the director theory, you have this universal structure. So, it would be interesting for one thing to find an analytic expression for it, and then to show that it's universal. And in order to do that, you always need to use that local energy minimizing assumption, because otherwise you might reach the melting hedgehog. Okay, now, in some sense, what is the most interesting for me and the core of this theory is to show that the energy minimizers display no isotropic melting. So the energy minimizers are overall, in most regions, close to the directors. So of course, they will display no isotropic melting. If they are to display isotropic melting somewhere, it will be in these special regions. But in these special regions, we have those melting hedgehogs, right? And there are these simulations of Chuck where you seem to see that there is no melting in those biaxial tori, right? So in this picture, alpha squared, this parameter here equal to 1 would correspond to melting. So, it seemed to me that it doesn't reach 1. So, can one prove this? Because this would make quite a difference. I mean, in Erikson's theory, and in Erikson's theory, the defects are interpreted as isotropic melting. So if you can show that, using this Q-tensor theory, you don't see isotropic melting ever, then defects must be something else, right? Perhaps this biaxial tori, perhaps something else. Okay, so we managed to prove this asymptotic expansion, which holds away from those exceptional small regions, away from those green regions. And now, the questions, the most natural questions are, what's the equation for the next order term? Yeah, because the next order term is really what makes the difference between Ozin-Frank, the limit, and between Ozin-Frank and the Q-tensors. The next order term is small overall. So you would say that away from defects, this tensorial correction provides no physical relevance. And the interesting question is if that's actually the case, namely, is this term physically relevant despite being small? Yeah. That's a question for physicists. If you ask Peter Palfi, he'll say no. But let me try to argue with that. First, there were two questions here. What are the equations for R, and is the term R physically relevant? The equations for R are messy. That's what we managed to do to obtain them. So there are like two parts. One part is okay, it's like an algebraic expression in terms of Ozin-Frank. And the other part is an equation that involves this first part and then the Ozin-Frank. Okay, so one thing that I should say is that the next order term has nothing to do with uniaxiality. Yeah, you would imagine that. I mean, this theory of Ericsson with uniaxiality is somehow squeezed between Ozin-Frank and Ericsson, and you'd imagine that you might find it somewhere there, but we couldn't see it at the level of these equations. So you can recognize Ozin-Frank theory out of the Q-tensor theory, but you cannot recognize the uniaxial theory at the level of global energy minimizers. Things are more subtle at the level of local energy minimizers. Okay, so I was trying let me try to get to the other question, whether there is some physics in this small correction from Ozin-Frank. And in particular, is there something interesting happening, in most of the region away from these defects? And there is this paper of de Gennes, types of singularities permitted in the order phase, and a physicist once told me that physics is more of a democracy than mathematics, in the sense that there are various theories, and the ones that get most citations and resist in times are likely to be correct. So judged by that metric, this doesn't look good. Right? So now I don't know why, but there is a small catch, namely this is not really the title of the paper. If you go to look for it, the title of the paper is actually Type de singularité permis dans la phase ordonnée. So it's in French. So that might be a reason for why I didn't get citations. The other reason is that perhaps physicists believe that is totally wrong. But what does it say? It says the following, that defects are discontinuities of eigenframes, of eigenvectors, right? And this makes sense from a mathematical point of view. Namely, you can have a matrix depending smoothly on a parameter, like our Q-tensors, which can have discontinuous eigenvectors. So this is, an expression that behaves like that. Yeah. So if I have, say, QL of this form, Q naught, which is uniaxial, plus a small correction, then I try to see, if there are discontinuities of eigenvectors. And I can actually draw these things using parallelepipeds, and it looks exactly like this. So if I look at this axis, I see these eigenvectors. I don't care what happens in the third direction, because you always have one constant eigenvector. I look along this axis, I see another constant eigenframe. So there is a discontinuity in eigenvectors in eigenframe here, where I'll have two equal eigenvalues, so I can choose any eigenframe really. So this makes sense from a mathematical point of view. You do simulations, and you actually see this picture, which is like half of that biaxial torus. So, it agrees with the equations. Now, the only team that needs to be happy would be the physicist team. And, if you do like me and go ask Peter Palfi, he'll say, no, that doesn't make sense, because the only things that you observe optically are just Q-tensors, not something smaller like eigenframes. But, I'm open to other suggestions that help with this.
Other suggestion in support of why the paper is not cited. So eigenframes might have something to do, but it's more eigenspaces. It's not necessarily Q-tensors, it's eigenspaces.
Yeah. What would it mean?
Eigenvectors have discontinuity, but eigenspaces don't.
Yeah, that's what I was trying to say with eigenframes.
So, the eigenspace, there's no discontinuity in the eigenspace. It changes dimension, but it's continuous. So if you think of eigenspace, in a way, so what happens is that one-dimensional merge into two-dimensional, and then two one-dimensional split in different directions. But it's a tricky question, what is exactly continuity of eigenspace, especially when they're sort of several-dimensional. But if you think of the entire space, not just the eigenvectors which span it, then there's no discontinuity in a way. Mm-hmm. If you think about, say, I'm not sure. So, but if you take operator norm for projection operators on those, I think that might be actually continuous, because it's just the trick. The trick that once
Yeah, I mean, I kind of understand what you are saying. Let me try to translate this graphically. Yeah, imagine that these are like ellipsoids instead of these parallelepipeds. Then the ellipsoids are continuous, right? There is no trouble here. And only if I insist at looking at their axes, I'll see trouble. So in some sense, I'm asking for trouble, but either some optical signature for this. I don't know. Dejean argued on basis of symmetry arguments, but he didn't actually try to provide some kind of experimental evidence or something. And of course, he didn't quite use this language, but Euler angles. But I think that the paper is pretty clear. It's just a 2-page paper. Okay, so nevertheless, from a mathematical point of view, this is an interesting question because you have these kind of troubles, in linear algebra. I mean, in numerical analysis, if you try to compute, eigenvectors near these points where eigenvalues, overlap, then you have serious troubles. And you also see things like this in quantum mechanics. I mean, one of my collaborators, Jonathan Robbins, recognized this from something that happened there. And you have something like this in hyperbolic conservation laws. But nevertheless, what can you say, assuming that that's a physically meaningful definition? What can you say about eigenframes, discontinuities? In order to have them, you need to have a situation like it happened there. Two eigenvalues become equal. So it's necessary to have this eigenvalue crossing, but it's not sufficient, right? So in particular, if you have a configuration like this, also discovered, I guess, by Peter Palfy, but the picture I took it from here, this would not display discontinuity in eigenframe, because the eigenframe here is continuous. What happens is that just the eigenvalues change, and you have a crossing in eigenvalues here. Yeah. So by the criterion previously mentioned, you have a situation when you have eigenvalue crossing, but it's not enough for having defects understood in the sense of eigenframe discontinuities. And understanding eigenvalue crossings is actually rather reasonable and simple at a mathematical level. You just look at this, modified Basque parameter, because, most of you know exactly that the real Basque parameter is 1 minus this term divided by this. But I like better this one because this is greater or equal than 0, and is 0 if and only if you have this increase in the symmetry, namely Q is either isotropic or uniaxial, right? So you could think of this if you want like weak defects. Namely, Dejean said that you need two things in order to have defects. An increase in the local ordering, so this would correspond to this, and also this discontinuity in what he called Euler angles. Yeah. And then he explained a bit that what he means by discontinuity in Euler angles is, for all practical purposes, eigenvectors. Okay, so now can you provide a criterion, an analytical criterion for checking if you have a discontinuity in eigenvectors when you see those eigenvalue crossings? Yeah. So when you see eigenvalue crossings, you might or might not have discontinuity in the eigenframe, and this is a criterion for checking that you actually have a discontinuity in eigenframe. It's expressed in terms of matrices, so tensorial. You want that this commutator is not 0. Yeah. So this is also in a very simple case when you have 2x2 matrices instead of 3x3, and in 2D. So then you can only have isotropic points where eigenvalues become equal. You can expand this to the 3D case when you have 3x3 Q-tensor but 2D domain. And the trick is to reduce, in some sense, to the previous case, as always. So first, you find a smooth matrix, so with values 3, so that you are reduced to this canonical form. And for this canonical form, you apply this commutator criterion, which, if you expand in terms of the initial thing, including R, becomes like some iterated commutators. You can do it, of course, for 3 by 3 Q-tensors in 3D domain, but then that becomes a little bit messier. But what I want to say is, okay, so if you assume that's an okay definition for defects, and you have that analytic criterion, how can you use it to see what happens in the case of interest? So this is the case of interest, where now I put instead of Q naught this Q star for the Ozin-Frank limit. Yeah. So you saw, earlier on that this small perturbation might create these discontinuities in eigenvectors which don't exist in this thing. So also, although this is a small thing, it creates that discontinuity in eigenvectors, right? So, okay, let me go back if you don't believe me. Here I have Q naught, no discontinuity in eigenvector, yeah? I put this small perturbation, the two of them together will have a line discontinuity when I interpret discontinuity in the sense of these eigenvectors, right? So although this is small, for anything that is non-zero, it still creates me trouble, yeah? So now the question is this, physical trouble or mathematical trouble? I mean, can you observe that small thing optically, physically? Okay, but at least at the mathematical level, if you are interested in what happens here, if you want to check this commutator criterion, you use this expansion and you get this. Well, the first thing here, should tell you what happens. If it's non-zero, then it doesn't matter when this L is small, then this is all that matters, right? However, this turns out to be 0. So the commutator condition for the solutions is something like this. So it involves the first order term in the asymptotic expansion. So you see some use for computing that term. And also if you want to check numerically what happens. So something that people didn't check numerically was, do you have discontinuities of eigenvectors outside of the biaxial course? And then the question is if that makes some physical sense. If you are to believe the Gen, I guess maybe, but 0 citations. Tomorrow I'm going to talk about a paper with 1,600 citations that I believe so much less than the one of the Gen. But this being said, what are the conclusions? The first conclusion is that I chose too grandiose a title for this presentation. I just talked about some things that are related to Q-tensors, the mathematical part that I understand best and for which there is technology. Tomorrow I'll talk about the part that I understand least and for which there is no technology, but very exciting nevertheless. So what happened so far? For global energy minimizers, things might change if you look at local energy minimizers. For very simple equations, you get this asymptotic expansion, and the first term is Ozin-Frank. What is specific to Q-tensors is encoded in this next order term, which is small pretty much everywhere except away from the defects of the Ozin-Frank. And the importance of this R term seems to come into these universal structures like the biaxial torus near the discontinuities in here. There you'll have that this term is actually order 1, not order L, where L is small, yeah. And away from the singularities of this Ozin-Frank, it might produce these eigenframe discontinuities, okay, which should only happen when you have regions which are uniaxial or isotropic. those regions are very small. You can prove that they have zero Lebesgue measure. Okay, now the uniaxial theory of Ericsson, which initially at the level of descriptors appears as squeezed between Ozin Frank and De Gennes, you don't see it here as doing anything good. Maybe something different happens at local minimizers, and you'll hear a very complicated talk about one of my collaborators, Valery Slastikov, if you go to Oxford to this workshop. Now, this is in some sense the simple questions that you ask, which have to do with what happens at a local level. Then the curse of dimensionality, the large-scale topological aspects are not mentioned here, but much more challenging, and we have a bit of a start in this direction with John Ball in that paper in ARMA. But that's still close to what is now understood about directors. If you go into the real thing, into unconstrained Q-tensors, then things are very hard to understand in a quantitative manner. If you do just topology, I think that what is done so far is pretty good. So, but if you want a quantitative understanding of the large-scale aspects, that's pretty tricky. And also tricky is what I'm going to talk about tomorrow. And that's in a very underdeveloped stage, but I'm hoping maybe I'll get some more intuition from the people here. So that's all that I wanted to say.
Very much for that. We have some questions.
Yes.
A couple of years ago, we did some work that is somewhat similar to this, in the sense that we realized that the bulk energy is dominant once you rescale the equations, and then that the evolution of the dynamics of the liquid crystal is on the manifold that corresponds to the minimizer of the bulk energy. And in that case,
well, I mean, in this case, we kind of do the other thing. Yeah, no, I think you're right. Okay.
My question was related to the R terms. That is, in our case, the corrections essentially were driving the dynamics of the liquid crystal on this manifold, and so they corresponded to the effect of the boundary conditions or an applied field. I didn't really understand what is the role of these R terms in this theory. Because you only have the boundaries.
Yeah, the boundaries are with R is equal to 0. Yeah.
Okay.
So if you look just quantitatively, what happens here is that things stay close to a Zinfranc to director pretty much everywhere, except on small regions. Yeah, those defects of the Zinfranc. But no, my question, and the interesting question, I guess, is this thing which is small, can you actually detect it? Does it have a physical signature? It's a mathematically interesting question. I don't know if it has any physical relevance, but I'm trying to throw everything on De Gennes and hope. But don't really know.
I argue again a little bit that if you go back to probability density of distribution of molecular orientations, so the general physically you'd be able to optically or by other means observe smallest moments of the thing, which will not. Well, eigenvalue discontinuity is eigenvector discontinuity. It's sort of, you can have an eigenvector which is x, and then you can have an eigenvector which is 2x. I mean, it's absolutely
no. If you normalize things, you put them.
Why would you normalize things? So my point is, I think I would agree.
Well, the way I think naively is that these eigenvectors have something to do with the special directions. When you say that material is optically biaxial, okay. So I don't really understand much of anything about this, but it seems that there are some special direction in which if you send polarized light, that doesn't change its polarization, right? And these are related to eigenvectors. So I don't know, are they?
They are, but they're also modulated. Any signal will be modulated by the eigenvalues. So essentially, as you go towards this discontinuity of the eigenvectors, you will also go to the zero signal connected with the discontinuity. So
but the point is, you don't need to have zero eigenvalues. You can have non-zero.
No, but the signal corresponding to the degeneracy of eigenvalues will go in some sense to zero. So it's essentially what I don't know. I would probably agree with Peter.
Okay. Also, there is this issue of order electricity, which might be related with variations in eigenvectors, but that's also something that I don't understand. So maybe some of you know about that.
Yeah, that has the same probably signature, I would think. But it's very difficult to detect, but I don't think that maybe one experiment is. You don't know. I mean, it's sort of a gradient of the magnitude of the order parameter, and then it's only on the second step dependent.
So I would have thought it's more like a gradient of the eigenvectors, but maybe, yeah, I don't know exactly. Yeah.
Also, I think if you have sort of slightly non-equilibrium rotation, it's fine. Q would fluctuate around, and there is absolutely no reason why the fluctuations would be uniaxial, even if the average field is uniaxial. So
Yeah, but this is just a matter of whether these things survive under perturbations and they are stable. They are stable under perturbations.
Sure. I mean, if you take arbitrary thermal fluctuations in the field of an actual liquid crystalline matter, so there'll probably be biaxial fluctuations. Why not? And then
Yeah, no. What I'm saying is about a certain type of stability. It's like this question: if I look at a zero of a function, is that stable under perturbations? Right? If I modify the function a bit, is that stable under perturbation? And you can have two situations. You can have something like this. Yeah, I modify the function a bit, I pull it up, not stable. But if I have something like this, now the zero is stable. So it depends, right? If I modify the function a little bit, perturb it, I still get a zero.
no, what I'm saying, assuming it's stable, assuming the isotropic, say, pneumatic phase, uniaxial pneumatic phase is stable, assuming that
Is what is?
is stable.
Yeah.
Locally. So then, if you
But it happens very rarely, right?
why not? I mean, it always happens, except.
Well, the thing is, it's a matter of terminology. If it's close to uniaxial, I don't call it uniaxial, okay? I only call uniaxial, which is exactly 2 equal. Yeah. So, of course, what's equal in physics and numerical
I think this
simulations,
relates to a question I was going to ask, because as a simulator, I'm used to fluctuations all the time. So I have particles moving around, and it's, let's say, a uniaxial liquid crystal phase. And I would expect to see in any region of space the two lower eigenvectors interchanging all the time, and the two eigenvalues crossing over. When I say all the time, really, I mean, it's not unusual to see that. But I guess what you're saying is that if I took a snapshot, I should expect to see that happening only in a very small set of points somewhere. And then if I take another snapshot some other time, it'll be happening somewhere else. But it's never happening everywhere.
No, definitely not.
I don't believe that.
Yes.
Hydra.
And so in trying to imagine an experimental situation where you might see R, might be able to see that signal, and I guess you want some distortion, which is on a very small length scale in order to change the order parameter. Distortion reduces order parameter. You can see that from the equations you've got. I guess one possibility is if you've got a chiral system with a very tight helix, tight pitch. So I wondered you haven't got a chiral term in here, but if you do have a chiral term in here, that would come into the R somewhere. And it might be that if the pitch is very small, you might see a reduction in order parameter. I don't know if you can see that experimentally. It might be something you could look at.
Yeah.
It's one way of getting a natural distortion without having boundaries imposing it.
Mm-hmm.
It's having a chiral system.
Yes.
Your asymptotic results all assume equal elastic constants, right?
Equal elastic constants.
Could you say something about the case when they're not equal, or what you think might happen there? Or whether there's just a technicality, or is it not a technicality?
Yeah. Various bad things would happen. At least, if you try to do things the same way, we're doing them now, but there is some work, of Patricia and Daniel, who, that they have some substitutes for, at a technical level for what we've done so far. So you might be able to get similar results, but I don't know what would be the difference. But it would be a technical.
But I guess the elastic constants only vary, I don't know, maximum, well, they don't even vary by doubling or halving. I mean, that's extreme. So compared to the many orders of magnitude difference between L and A, B, and C, that kind of change in difference in elastic constants probably wouldn't have a huge.
I mean, there is also this study of Chuck that I showed, those pictures of the Basque torus. He had there two elastic constants, right? And pretty much qualitatively the same thing.
Yeah, as near as I recall. I mean, we experimented. But you don't see any quantitative changes, no qualitative.
Yeah.
I saw Claudio with his hand up.
Yeah, on the issue of the elastic constant, I remember an old paper of Eugene Terentiev and maybe Oleg, I'm not sure, but there were two cases where an indicator, which was a combination of twist, play, and bend, which would be actually negative in the case of the three elastic constants being equal. It was something like 1/2 K22 plus K33 minus the other. And if that is negative, they were predicting an hyperbolic defect in this. And if it was the other way around, a joke. In these days, we used to call it a joke. Now, we did simulation with the Bibo-Lasher model, which actually has equal elastic constant, and found a region which was more similar to a kind of ring. It was published. It was with Tim Looking a long time ago. I can pass the paper.
But on small, well,
Point
everything is small there.
Sorry?
No, I was just wondering how large that region was.
But it wasn't that large because it was a long time ago, but it was small. Actually, the size of it's a long time ago, so I will check. But I think the point was that the core of the defect was of the order of the coherence length of the nematic side, rather than being much bigger. But the other thing is...
So that's consistent with this biaxial torus. That's exactly what they see.
It is consistent with the biaxial torus, and we compare with, I think, with Trebin had also a paper, and Pentha started there or something. So our is a simulation. Again, simulation is different thing. This is Monte Carlo simulation from bottom up on a microscopic model, not a simulation
a continuum level, yeah.
at continuum level, which like Hess and other people here actually have done. It's a different type of simulation, even though the equations are similar. But then we do have the problem that Mike was mentioning of statistics and fluctuation, etc. And for example, if you have a situation with different defects in the same region like you had there, then they could be oriented in different ways if you have a non-point defect. So we found useful to calculate suitable rotational invariant quantities, like stone invariant, like rotation invariant combination of Wigner rotation matrices we used to calculate T222. And if you could find rotational invariant quantities that are different for the different situations that you envisage, then this would be something that one could calculate and test with microscopic simulation independently from the optical argument that they were used before. In other words, if you have, if I understand your, eigenvector discontinuity, what kind of discontinuity do you have?
Yeah, if it makes any sense.
If it is anything, then it would be difficult. But if you predict that you have some sort of structure and that this structure has different rotational invariant associated with it, then we could calculate them.
I have to think about it.
Well, suppose, for example, I take a stupid example. Suppose that they clash in this way. So you have a uniform domain here and a uniform domain here. So the eigenvalue is still positive. It's actually the same, because it's the same. But they have the kind of orientational grain boundary here. Is that what you mean by discontinuity of the eigenvector, I think?
Yes.
Right? Then in this case, it would be a kind of 90-degree type of structure. And if I build a suitable rotational invariance, I could pick up all the cross-type situation across my
Right, but I mean, you rotate that, so you get that ring.
Well, okay. Yeah, but if I build a rotational invariant quantity, a ring like this, or like this, or like this, like this, would contribute in the same way, and we could actually measure it. Well, simulate. Maybe we can.
Yeah, maybe we could.
It wasn't
I don't
clear.
really
But it seemed to me
understand.
that it would be useful to have something that one could compute,
Yeah.
and not just.
Sure. I have something in terms of Q-tensors, but that's not what you want.
But you had the test. I only saw what
Yeah.
that it was in 2D, wasn't it?
You can do it in 3D. It's just more complicated.
And the other, if I may, just a simple thing. Can you make different prediction for rank 1 order, so for the magnetic case, where the behavior is totally different, or for the rank 4 case, where you also can have microscopic interaction of rank 4 rather than rank 2? What
If
would
you adopt this definition with eigenvectors, yeah, it's just a mathematical extension. It's not no big deal. They will be more and more complicated
For
as
example,
you increase the rank.
with the rank 1, the magnetic, you have a true hedgehog, you have a true.
True eigen.
You cannot actually obtain the torus or whatever.
Okay.
And so maybe you can make different prediction for different rank, which could be.
Okay. I'm not aware of this, but probably I'll get
So
some
if you have
references. from
magnetic
you.
domains, the type, because you don't have, you have a true vector in that case.
Sorry.
In the case of, if you have, rather than nematic particles, or imagogenic particles, you have spins, you have true spin. You have an Heisenberg model, say,
Okay.
magnetic model, then, the defect, I mean, maybe Epifanio, you remember, the defect is different, and it is a true point defect.
Right. I don't really know anything about that, but probably I'll get some references from you.
Okay. Don't forget, tomorrow we have 2 seminars, both in the small seminar room, I'm afraid, in the Gatehouse building. So let's just thank Arghir once again.